In this subject, we're going to use some matrix algebra to help simplify our discussion of some of the issues involved in regression models and panel data models and so on. This video will introduce just some of the very basic ideas of matrices. In particular, we're just going to detail what is a matrix, what is a vector, how you transpose them, add them, subtract them, multiply them, and end up with writing down a regression model using some matrix algebra. For some of you, this will be all very easy if you have learned matrices before. So if you grab the notes for this overhead and have a scan for this video and have a scan through them, and you find that this is all incredibly simple, then you don't need to sit through this this video. If you haven't seen matrix algebra before, then this video probably is for you, because we're going to start from scratch and go very slowly through the basics. And if you haven't seen matrices before, I do recommend that you either sit through this video or somehow or other acquaint yourself with the basics of matrix algebra, because we are going to be returning to this throughout the semester. First of all, a matrix we can think of as just being a rectangular arrangement of numbers surrounded by some brackets. So here is an example of a matrix. A is a matrix that contains these 6 numbers. Every matrix has a dimension, a number of rows and a number of columns, and it's generally important to keep track of those dimensions, the rows and the columns. In this case, A has 3 rows, okay, 1, 2, 3, and 2 columns, 1, 2. And we write the dimension of a matrix as, for example, 3 times 2. So the rows always come first. And it's important to keep track of dimensions of matrices when you're dealing with them. They are important, and can avoid mistakes if you keep track of those dimensions. In addition, we will on occasion talk about individual elements of a matrix as subscripted by an I and a J. And again, the row comes first. So if we want to talk about the element in the second row and the first column, which is the 2, then we would denote that as A21. Okay, the second column and the first row is equal to 2, or the third row and the second column is equal to 6, and so on. Now we have a special type of matrix which is called a vector, and a vector is simply a matrix that has a single column, has one column. Sometimes we might call that a column vector, but if we just say vector without the word column in front of it, the word column is assumed. If we want to have a row vector, which consists of a single row, then we would always put the word row in front. So here's a couple of examples. B is a vector, it's a column, okay? Whereas C is a row vector. It goes across, it's a single row. So this is a 2 by 1 matrix, or a vector, and this is a 1 by 3 row vector, or matrix as well. The other bit of terminology that we will have is a scalar, which is just the word for a single number. It's a 1 by 1 matrix. Okay, so it's a special case of a matrix and a vector and a row vector is a single number. Now, the idea of a transpose is it's an operation that we use a lot, which takes a matrix and turns all of its columns into rows, and equivalently rows into columns. It's kind of like turning a matrix on its side, if you like. And the transpose is denoted with the prime notation. So if we start with a matrix with R rows and C columns, and we take its transpose, then what we end up with is a matrix with C rows and R columns. Okay, because all of the rows have become columns and the columns have become rows after we take the transpose. And there's a couple of examples. So remember, the A matrix, for example, consisted of these elements. Okay, so the 1, 2, 3 column will become the 1, 2, 3 row, and the 4, 5, 6 row, and so on. Okay, so we're just going to flip the matrix on its side. The column vector has become a row vector when transposed, and the row vector has become a column vector when transposed. If you transpose a matrix twice, you get back to where you started. Okay, so if we transpose this matrix again, we would return to the original A that we had. If we transpose a scalar, that does nothing. So this transpose of any single number is just the single number itself. Which seems a bit silly, but there are times when it's handy to remember that. Now, there are some special kinds of matrices called symmetric matrices that we meet from time to time in econometrics. They're important. To be symmetric, a matrix first of all has to be square. And you can probably guess a square matrix is one which has the same number of rows as columns. So this matrix M here is square because it has three rows and 3 columns. Now the matrix is symmetric if it's equal to its transpose. Okay, so M21 is equal to M12. Okay. And M31 is equal to M13. Okay, so that's the symmetry in these zeros as well. Okay, M32 and M23 are equal. So the symmetry tells us about those. It doesn't tell us anything about the 1, 2 and 3 down this main diagonal of the matrix. Okay, so this matrix, if a matrix is symmetric, it's like it's kind of been reflected around this main diagonal. Now the main diagonal, which I've just been talking about, are the elements running from the top left to the bottom right. Okay, so 1, 2, 3 is the main diagonal of this matrix. So that's the elements M, I. So we'll refer to that on occasion as well as we go. Now, the rules of arithmetic for matrices. They're not terribly difficult, but there's just a few factors to be aware of that are not relevant when we're just dealing with numbers. Two matrices can be added and subtracted only if they have the same dimensions. Okay, if two matrices have different dimensions, then there is no sense in which we add them or subtract them. So if they have the same dimensions, we say that they are conformable for addition. Once the two matrices have the same dimensions, then adding them and subtracting them is easy. So here's a matrix A that we've seen before, here's another matrix D. They have the same dimensions. They're both 3 by 2 matrices, so we can add them. Okay, 1 plus 3 is equal to 4 here. 2 plus 2 is equal to 4. 4 plus 8 is equal to 12, and so on it goes. So you just go element by element, adding up the individual elements of those matrices and arrange them like that. A minus D works the same way. 1 minus 3 is minus 2, and so on that goes as well. Okay, so the addition and subtraction operations themselves are simple. Just need to make sure that the matrices are conformable, otherwise they don't make sense. We can take a matrix and multiply it by a single number very easily. So if X is a single number and A is a matrix, then we simply take the matrix and multiply every element of it by that number. So here, if A is the matrix that we saw before and X is 2, then we just take all of the elements and multiply by 2. Okay. So that much is easy as well. Now, matrix multiplication, multiplying two matrices together, is a bit more involved. So let's suppose we have two matrices, A and B, that we want to try to multiply together. And the dimensions are important. We need to keep track of these here. So A has dimensions RA times CA, okay, rows, columns, and B has dimensions RB times CB. Now, we can multiply A times B if the columns in A match the rows in B. They're the same number of columns in A as there are rows in B. So if you write the matrix A and the matrix B and you put the dimensions underneath those two matrices, what we need is for these two here that are next to each other, they need to match. If those two match, then we can do the matrix multiplication. If they don't match, then that matrix multiplication is not defined. We can't do it. The result, if that's true, if those two dimensions are equal, the result is a matrix A times B, and that has the dimensions given by these outside dimensions. The result has the same number of rows as A and the same number of columns as B. And the individual dimensions of this product has a formula that looks like this. Now we won't dwell on that formula because I don't think that's all that illuminating, but we'll just show some examples instead. So here, here's two matrices, A, which is our original matrix, and B is a 2x1 vector. Now we can multiply A times B because A has two columns and B has two rows. So they're conformable for multiplication. So A, B is defined and we can go ahead and do it. And here's how the operation works. We basically proceed by multiplying the rows of A by the columns, in this case the single column of B, by which I mean we go 1 times 1 plus 4 times 2. Okay, so when we're multiplying matrices, it's actually a mixture of multiplication operations and addition. Okay, 1 times 1 plus 4 times 2 gives the 9. Okay, 2 times 1 plus 5 times 2 gives the 12, and so on. So that's the basic operation of multiplying matrices together, this mixture of multiplying the individual elements as they match up and then adding up to get the final results. Okay, then the final result is a 3x1 corresponding to the 3 rows in A and the single column in B. Okay. Now with matrix multiplication, the order in which you write those matrices down is important. Okay, this is not the case when we talk about numbers. Okay, whether you go 2 times 3 or 3 times 2, you get the same answer, right? When we're talking about numbers, multiplication is commutative, doesn't matter the order. But with matrices, the order matters. Okay, in general, matrix multiplication is not commutative. So in this case, A times B is not the same as B times A, and this is generally true. If you take a look at these matrices here, we can't even do B times A. We can't even do B times A because B has a single column and A has 3 rows. So B times A is not possible, whereas A times B is possible and has an answer. Okay, and so most of in general, AB and BA are different. It's only in very special cases do they actually turn out to be equal. Here's another example where we can multiply the matrices in both ways. So B, remember, was our column vector, 1 and 2. Okay, so if we take the column vector 1 times 2 times the row vector E, which is 2, 3, then we have a 2x1 matrix or vector B multiplied by 1 times 2 row vector E. So that's conformable. We can do the multiplication and the result is this 2x2 matrix here. On the other hand, if we multiply them in the other order, E times B, then we have a 1 times 2 matrix multiplied by 2 times 1. So the result is a single number. Okay. So in this case, we can get an answer for B times E and E times B, but clearly the answers are different. And that's usually the case. So be careful with matrix multiplication that the order is written down the right way. If we want to take the transpose of a matrix product, as we will want to on occasion, then there is a simple rule for that. If we want to take the transpose of a matrix product, assuming that the matrix product is defined, then we take the transpose of each of these individual matrices and we reverse their order. Okay, so AB transpose is equal to B transpose times A transpose. So that reversal of order is important in this formula. Okay, if you just said AB transpose is equal to A transpose B transpose, that would be wrong. Okay, that's not the formula. Here is an example, a numerical example, just showing you that it works. Okay, so B transpose is turning the previous column vector into a row vector. A transpose is the A transpose matrix that we've seen before. And then we go 1 times 1 plus 2 times 4 gives us the 9. Okay, 1 times 2 plus 2 times 5 gives us the 12. 1 times 3, 2 times 6 gives us the 15. So we get the same numbers as before, but now they're arranged as a row. Okay, remember last time they were arranged as a column. So we've got the transpose of the previous answer as the formula has suggested. Okay. I'm showing you these rules and these definitions illustrated with these kind of numerical examples here, just to show you them working. From our perspective, once we've got these rules written down and learnt and understood, I'm not going to keep coming back and asking you to do these little numerical examples. These are just here to aid your learning. What we really want these matrix definitions and operations for is to be able to represent regression models and their developments that we're going to look at throughout the semester. So here's our first simple example of that. Here we have a PRF, a population regression function, which is a conditional expectation. And in this case, it's a multiple regression model. So we have the conditional expectation of y given k explanatory variables being expressed in terms of an intercept, and then those k explanatory variables with the coefficients beta 1 up to beta k. Okay? So this is a standard multiple regression model. You've seen these before, right? All that we're going to do now is to take this PRF, this regression function, and express it in matrix or vector notation even. So to do that, we will take all of the explanatory variables and stack them up into a single vector called xi. And here they are. Now we have the 1 here. This 1 is corresponding to the intercept. There's kind of implicitly a 1 sitting after that beta naught, okay? And then the x1 dot 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 xk. So that vector, it's a k plus 1 times 1 dimensional vector, contains all the explanatory variables. And corresponding to that, we'll define a vector with all of the individual coefficients, beta naught, beta 1, up to beta k. That's the same dimension, k plus 1 times 1. Okay, so we'll define those two vectors, and then we can represent this PRF, this linear function on the right-hand side here, simply as xi transpose beta. Okay, so xi transpose will take this column vector and turn it into a row, and then when we multiply that by beta, we will get 1 times beta naught plus x1 times beta 1 plus dot 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 xk times beta k. So it simply returns the PRF back to us that we started with. So the point of that little maneuver is that we can now write the PRF for any multiple regression model quite compactly as the expectation of y given the vector x as being xi transpose beta. Okay, and this kind of representation turns out to be very useful for writing down, OLS and other estimators and working out their properties and stuff like this. Dealing with those in the matrix and vector notation is far more convenient than just writing out everything individually as we do here. Okay, so as we go through the semester, we'll be seeing lots more of that. So it's worth starting at this stage early in the semester, getting on top of just these really basic operations with matrices and vectors.